Okay, so today we will have lecture 6. Now, till now we were reviewing, in fact. I assumed, okay, all of you have some background, and then we were reviewing some basic concept that you need to follow up. So now, actually, we will start mixed signal universe from today. So first will be sample data filters, again, which are used a lot in mixed signal systems. So, and these are the topics hopefully we can cover today. One is the finalized review of continuous time filters, and then talking about basics of sample data systems. What are discrete time frequency transformations? How we can go from continuous time to discrete time? How you map a design that you do in continuous time to a design in discrete time? And then after this mapping, then it will be implementation. Therefore, we will start talking about how switch capacitor filter are one of the best types of discrete time filters. So before that, just as a reference, so I asked Viral to prepare a brief design procedure for elliptic filter from Williams' handbook. So don't care about these values. He has just kept some values as an example. But essentially, this is the elliptic filter configuration. And of course, you will see today, it's very interesting. As I said, because phase can be compensated in digital, therefore, if DSP compensates for the phase, therefore, elliptic filter will be the best and more economical type of filter. But you will see, as soon as you want to implement an elliptic filter or any sort of sharp filter in discrete time, go with sample data system, the first thing you will observe that sharpness will go away. The reason is you cannot have ideal sampling. Therefore, we will have practical sampling. And practical sampling doesn't transform continuous time frequency to discrete time frequency in a way it should. Therefore, what happens is, then we will have distortion in the frequency transformation, and that leads to all of problems. So then it is actually a nightmare, because you design everything very well in continuous time. As soon as it comes to the discrete time, then specifications are lost. Even this zero attenuation, in fact infinite attenuation or zero transfer function will be lost. But it is interesting to see how we can avoid it. Of course, as long as, say, audio signals are concerned, there is no problem. As long as, for example, you have separation between channel in a wireless receiver, there is no problem. But if the number of channels are high, or for example, you want to have different video signals, then actually there the problem occurs. Because there you cannot have a very well separation between two adjacent signal or channels. So we will see how it will affect. Okay, so this is, I don't know whether it is clear or not. No, here is clear. So this is RDB, is the ripple you get in the passband. You will have one parameter which is A mean, means that when I want to go from the maximum value of transfer gain, which is 0 dB, to the maximum allowable transfer gain in the stop band, this difference is called A mean. So for the sake of design. And as one of you asked, see, this 0 dB is the normalized transfer function, which is used for implementing ZE. This is not the real transfer function. Real transfer function in a passive ladder will be 1/2 at low frequency maximum. Okay, so now we have two parameters. This band is normalized to 1. Therefore, in stop band, you will have omega s. So we have now three parameters, RDB, A mean, and omega s. So accordingly, these values we need to know, or we need to derive from whatever requirements we have for the filter. And of course, termination, again, we consider to be equal. As I said, if they are equal, then we will get the minimum sensitivity. Otherwise, a cascade of backward will behave better than a ladder. So, but with this, we can get a very good low value of sensitivity. So, how to design? First, we compute a stiffness factor. Stiffness factor means that how much the edge in the stop band and edge in the pass band are separated from each other. Therefore, this ratio will be stiffness. And then accordingly, we will have one more thing, because when we normalize the frequency in such a way, in pass band it will be 1, therefore in the stop band it will be something like omega s. So omega s is actually that ratio of this frequency to this frequency, this two corner frequency. Therefore, it determines there is a parameter theta, sine inverse of 1 upon omega s, which will determine the stiffness of the filter. Okay, so now we will have these two. So normal AS and theta. Then RdB was the repel. RdB is related to reflection coefficient by this relation, and this is actually 1 upon H. This is H, rho square is 1 minus rho square is H square, if you remember from the relations. So this is in fact the amount of attenuation in the pass band. Accordingly, there will be a parameter which will be in fact 20 log of 1 upon rho, which will be used in this plots. So then you will have this A mean, which was defined here. So now using this A mean plus AP, which is found from RdB, and omega s, which is stiffness of the filter, you can derive order of the filter. So one direction you will see the one axis is omega s, one axis is A mean plus a P or a rho in fact, which is defined like this, and N, order of filter. Therefore, accordingly, you can get order of filter. Because if you know omega s, you know A mean plus A rho, you will get order. This order may not be integer always, but you want to be integer. Therefore, that's why they have plotted some of the plots for different values of order, so that in the vicinity of some specification, you can get integer numbers. For example, 2 here. And then if you shift to left for 150, if you go to the higher plot, which is 4b, you will get again order of 5. So in this way, this gives freedom to you to reach to integer values for order of filter. Therefore, for example, if omega s is 2, sorry, not 150, 1.5. If omega s is 2, for this amount of A mean plus A rho, which is around, say, should be close to 50, is 4. If you reduce it to 1.5, you go here, you will get 5. And here, order of filter is 6, and here is 5. So accordingly, you will get order of filter. So till now, you know order of filter. Then what you should do? You should determine value of L and C. So that you will do by using this charts. So you know theta, it is calculated. It was a measure of stiffness, and omega s, and A mean. So according to these three values, you will get L and C for the entire filter. And then you will denormalize. When you want to denormalize, we will use the same relation that we had for L denormalize and C denormalize. So it's same thing. You have this 2 pi fc, which was omega c in fact. And if you remember, for denormalization, we would define an impedance, which was this fc, multiply the impedance we have. Accordingly, you have this c, you will get c denormalized. For example, impedance in this case is 900 ohm, right? Termination impedance. So you have 900 ohm multiplied by this 2 pi fc, c divided by this, and L multiplied by this will give you L denormalized. So accordingly, these two values will be obtained. So this is a very straightforward way of doing that. So then now you can repeat the same assignment now by using these tables. Any question? Is it clear? Okay, so this is very straightforward. So few things that remained from last lecture, I will finish them and then we'll switch to sample data systems. So we had an example of multiple feedback, which was showing a very good way of controlling Q, right, from last lecture. And we had this biquad. So in general, for a low-pass biquad, we can write it in this form. So then one way of implementation was using a all multiple feedback second order biquad. So this we did in the last lecture, and then you observe that almost Q is independent of process variations, which was a very good example for this type of filter. Now in general, if you don't look at how Q and omega 0 is related to the filter specifications, because as I said, one way will be to use these biquads. Each one of them will have its own tuning mechanism. Then we can implement a high order filter. As long as we can implement multiple feedbacks inside the biquad, then we would be able to get low sensitivity. Therefore, it can be one of the replacements for multiple order direct LC ladder simulation because of its in fact simplicity and better way of controlling parameters, because you know exactly how each component is related to Q and omega 0. However, if you want to design for a very short filter and therefore you will have a very high Q biquad, and again that has conflict with the purpose you have. Why this happens? The reason is because if you look at like amplitude of edge, therefore if you increase Q of filter, you are losing what you had. You were expecting from this filter. You wanted to have less sensitivity, but now you have this problem. Why this problem happens? Specifically, as I said, this problem happens in the transition band. If you remember from last lecture, in the multiple feedback biquad, transition band was sensitive. In fact, we could control, no, actually it was not. Q was controlled by the ratio of capacitors. Omega 0 was a function of RC, therefore we had variation. So in that case, it was okay. So now, in general, what will happen if you have variation? How it will affect on the specifications of filter, which is very common for on-chip. So we will obtain the sensitivity of this parameter, P, the same way was defined in the last lecture. So this is sensitivity as we defined. So what you need to do is so this is omega. What you need, just you take derivative of this with respect to omega. So I don't write it, and the final value will be this. I have used 1/4 and here 1/2. The reason I did it because in implementation, using passive components, it has a value of 1/2. So just to make sure that, see, this is not the normalized transfer function. This is real one. So that's why I just kept it. And I have used that, therefore final value will be 4 omega upon omega 0 square, 1 minus omega square upon omega 0 square, plus 2 omega upon omega 0 square into 1 upon q square upon d omega. And d is the denominator. It can be LC also. See, you can implement a second order LC and then convert it. Yeah, yeah. This just I kept because to say that, okay, if we consider we have an LC and we want to get it from an LC, then this will be the value. Because I have used 1 upon 2, if I remove it, then I have to calculate again. Of course, it doesn't affect because, yeah, practically it doesn't affect. See, if you make this 1, then this also will be 1, then I will get this. No, it doesn't affect. Sorry. Okay, so then this will be the value of the rod. And finally, if I simplify it, and D is denominator of this transfer function, magnitude square of transfer function. Now suppose Q is very high, okay? So if Q is high, now if we have at one particular frequency, right? Say for example, I have a particular frequency, particular component which affects on my omega 0, right? Therefore, at particular frequency omega equal to omega 0, if I want to see, I have a component, usually this omega 0 is a function of some RC values in general. Oh, so if it is an active RC. So I want to see, like, if I change this value, how omega 0 will change if Q is very high. So when Q is very high, so if you look at this denominator, when Q is very high, this then will be very small. And therefore at frequencies close to omega 0, if I want to see at some particular frequency like omega 0 or omega star, which is close to omega 0, which will be close to peaking frequency, what will be the variation of this? So this term will be very small, this term also will be very small, therefore magnitude is very high. Accordingly, here also, here if you notice in the numerator, we don't have anything specific. So it will be some specific number because Q is large, therefore this term will be small, and here we will have 4 omega upon omega 0 square divided by this d omega. So now this term will be very large. So 1 upon d omega will be very large, so this will increase as Q increases. So if Q goes high, then sensitivity of this magnitude with respect to some frequency close to omega 0 will increase. Therefore, even if we are able to control the Q, as we increase the Q, we will have problem with the shift of omega 0, and shift of omega 0 is a big problem. When we want to have the best attenuation for adjacent channel, or for example, if you want to have to apply it, to use it as an anti-aliasing filter. Therefore, you need to have a very well control of bandwidth. Therefore, omega 0 should not shift. So that's why usually designing by quad with a very high Q is not recommended, just because of high sensitivity of peaking frequency and frequencies close to that frequency. Yes. Yeah, that's why it's very high. And because this term also is very low when Q is high. I didn't neglect. I have written it. Just the omega. Numerator is plus. This is approximation.
In that bracket, that is 1 minus omega square upon
This one. Okay, you say numerator also becomes a small. Okay, okay. Mm-hmm. Yeah, yeah. Okay. But then you recalculate because it should show this performance. Maybe I have made somewhere a mistake. You double check it. See what you need to do. You just one thing you can do instead of thinking derivative with respect to omega, you just make derivative with respect to omega 0. This d omega. Yeah, this is h square. Okay. This one. Okay. D omega square. Yeah. Okay. Let's calculate it. Let's calculate. It will be fast. We'll calculate. You calculate it also. I will also calculate. This is P. Right, we can consider omega 0. And then because when it changes, when the component value changes, omega 0 will change. Therefore, how this magnitude will change? Or we can calculate it with respect to omega and then consider, okay, now if frequency is close to omega 0, how it will change. Let us make it omega in general. So this will remain. So it doesn't go away. Because of ratio. Okay. So now sensitivity of P to omega. So I will keep this numerator same as before. This is 1 upon P into omega. It will be 2 omega square 1 omega 0 2 This will be 2 into 1 minus omega square upon omega 0 2 minus 1 upon q square. Correct? Yeah. So now if you, for omega close to omega 0, and when q goes high, this sensitivity factor will increase. So whole purpose just is to show that when q increases, they have to be worried about sensitivity. And effectively means process variations. That's why, as I said, it's impossible to design specifically at high frequencies without any tuning. See, for example, coming back to the last lecture. My lecture notes. So in the last lecture, for that multiple feedback, okay, this was the filter. Omega 0 was 1 upon RC. If you remember, look at your notes, it was 1 upon RC, okay? So how this will change? Say, for example, R will change by 10%, C will change by 10%, therefore omega 0 will change, worst case value, right? Therefore this will be 1.1 into 1.1 RC. So this will be 1 upon 1.21 RC. And how much this will be? Calculate it. Have a calculator in the class. Yes? Close to 80%. Therefore, this will be around 0.8 omega 0. Say nu. So you will have 20% change in the omega 0. So how sensitive it is determined by the Q. Here, this is in general, okay? If we increase Q, this sensitivity factor will increase with respect to parameter omega 0. This multiple feedback has the benefit of Q was the ratio of root square C1 upon C2. Therefore, we had one freedom to control Q independent of omega 0. What you want to say that in this special case, sensitivity is independent of Q? Yes. Suppose, for example, if C1 changes by 10%, as we have shown there, C2 changes by 10%, and R also changes by 10%. So Q will remain constant, but RC2 will change by the value of around 20%, 1 upon RC. Therefore, but look at, this is variation of omega 0, but look at the variation of HJ omega. So if Q is high, if you change omega 0, then this term will change drastically, right? So it's sensitive to omega 0. Because I want just to look at some range of frequencies around omega 0. But if you want to look at only omega 0, yes. But these two should give same results. If you differentiate with respect to omega and then replace omega by omega 0, if at the beginning you differentiate with respect to omega 0, these two should give same results. Yes. But that there also you need to look at the variation in the transition band. Transition band means again omega close to omega 0. Then again you will replace omega in the second one by parameter which is close to omega 0. Yeah, see. This is the transition band for a low pass high Q filter. It will be like this, right? And omega 0 is not always the peaking frequency, but it will be close to peaking frequency. So it's something like this. Now, if you change the frequency, the parameter, so omega 0 will change, considering Q will remain constant. If Q remains constant. So I want to see that how sensitive will be this transfer function in the transition band to omega 0. So if I want to see, if you want to see sensitivity of transfer function to omega 0, then means that this is how this magnitude changes with respect to omega if I change omega 0. Another way I will say that I want to see that how this magnitude changes with respect to omega when I am close in the vicinity of omega 0. So these two should give same results. If you see, we want to look at the transition band, specifically this area, right? If you get derivative with respect to omega 0, then you will see how Hj omega will change with respect to omega 0, how sensitive it is. Now it is omega, therefore it's a variable. Now you want to see for a particular frequency how it will change. So that particular frequency is in the vicinity of omega 0. Then you will replace it again by a frequency close to omega 0. That is an interesting point. In fact, these two should be same, similar. But suppose if you want to see how Hj omega will change at this frequency, for example. How Hj omega will change if I change omega 0 at this particular frequency. Then here I have to take derivative with respect to omega 0. Because my omega now is far from omega 0. Essentially, it's better now because it was discussed. I tell you what are this type of filters. Even intuitively, you can see how it affects if I increase Q of filter. Do one thing, you calculate both of them. Yeah, that's a good point. You calculate, see whether how they are different. But for omega close to omega 0, around omega 0. And then 1 upon omega 0 Q, we can write it in the form of zeta omega 0. And we define zeta, okay? So now, if there is a peaking, this is also just a reconfirmation of what I wrote in the last lecture. So this will be the peaking value. So it depends on the zeta. What is the range of zeta for this purpose? This happens only when Q is greater than 1 upon root square 2, or in other words, if zeta is less than 1 upon root square 2. So in that case, we will have peaking. And the frequency at which this peaking happens, we call it omega max. This will be omega 0 root square 1 minus 2 zeta square, which is less than omega 0. But if you reduce omega zeta, means that it will approach to omega 0. That is the point I am saying. If you increase Q, your zeta will reduce, and then your omega max and omega 0 will be close. So if zeta reduces, zeta is equal to 1 upon omega 0 square Q. In other words, if Q increases, then omega max will approach to omega 0. Q increases. If you increase Q, zeta will reduce. So this is in the direction of increasing Q. Or decreasing zeta. Particularly if zeta is equal to 1 upon root square 2, which is the boundary, omega max will be 0. This is the boundary at which we don't have any peaking and it starts peaking. Means that it will start at omega equal to 0, then it will shift to omega 0 as we reduce it. So means that here it will be like this. Omega max will start from 0, will shift to right till it will reach to omega 0. So this is zeta mean. Yes? Here? Oh, okay. Okay, call it zeta. Okay. Fine. Again, this will be zeta. Oh, everywhere you convert it to zeta. No problem. So see, no, now you look how this is sensitive to omega 0. If Q is very large, okay, so means that zeta is small, right? So omega max is proportional to omega 0. If you increase it by 10%, omega max also will increase by 10%. And this omega 0 is a function of components. See, other values, it depends. For example, if you make a cascade, still each one of them has the same performance, right? But if you make a ladder, it's not exactly like this, but trend will be same thing. Because see, you have the maximum variation or sensitivity to omega at transition band, right? Always transfer function has maximum sensitivity to variation of omega in the transition band, right? Look at omega as a parameter. Okay, that's why I took derivative with respect to omega. You know, if you look at a filter always has maximum sensitivity with respect to omega. Yeah? Frequency itself at this transition band. Any sharp filter. Therefore, doesn't matter second order or nth order. Therefore, we expect always the maximum sensitivity to happen in this range. And when this is sharp, means that this is sensitive to omega. Therefore, in other words, if you keep omega constant, change parameters, keep parameter constant, change omega. These two should behave in the same manner. So, this is the way, in fact, I explain it for myself. Like to, really, what is the reason behind that intuitively? The reason is it is simple. It's very sensitive to omega. So, we would expect in higher order filters, even if it is ladder filter, always if we increase Q, we would get more sensitivity in the transition. Yeah. So, trend may not be same in the sense that sensitivity value percentage may change, but trend is same in the sense that always it will be more sensitive in the transition. Therefore, what I do is, I consider, see, we have a filter, it has some parameters, Pi, so you keep constant Pi, change omega. Or you change Pi, keep omega constant. These two are in fact same. Transition band is where my omega is close to omega 0. Therefore, in the transition band, always I will go from a very high value to a very low value. Therefore, I have a limited, in fact, range for variation of omega. So, if parameters change, therefore, this my limited range will change. I will have sensitivity. Omega 0 will shift to left and right, even if I keep Q constant. See, when it comes to stop band and or in this region, if you are talking about this region and this region, I don't know. I cannot say that with real stop band will be more sensitive compared to pass band. So you mean that because this shifts to right or left, but when it shifts to left, then you know this H also will see a lot of variation in the transfer function. So when Q is high, definitely you will see this type of variation. See, when Q is low, you have a flat transfer function. So if it shifts to left, and when it shifts to right. So let's see, like for the maximally flat. And suppose this should have been my omega s. And this should have been my omega. So now, by this, I will have this. It is shifted here. So as at this frequency, now I have this. See, in a passband, you may say that, okay, absolute value of this is more. But the point is, in a stop band, we have higher attenuation. So if I get 5 dB, 6 dB change in a stop band, but if I get 1 dB change in passband, 1 dB change in passband, this might be more important for a designer, right? Yeah, increasing Q, now if you have Q, then you know what happens is you have such type of transition, right? Therefore now it, even Q, if Q is constant, like multiple feedback, but then you shift, corner frequency definitely will change. But the point is, even in the in the passband or stop band also, you will see the effect. But here now, in the transition band, the effect will be more because you have more the change of the amplitude here. Here in the transition band, how much do you have change in the amplitude? Say it can be 3 dB. But if you have peaking, this can be more than that. And 3 dB, of course, is too high. It will be less than that. You need less repel in the passband. But if you have a Q, you want to have a very high gain at some particular frequency. And then now if omega 0 changes, then suddenly you will have a huge drop in that frequency. If this peaking is important, means that this peaking is used as some sort of bandpass information. But if this Q is not important, this jump is not important, then automatically you are ignoring that part. So then it's not sensitive. Sharper transition, higher peak. These two are together. No, they are together. Means that if you want to get sharper transition, you will have more repel, or it can be peaking, it can look at it as a repel. So you will have more variation in the passband. These two are always together. And because they are together, therefore high Q will give more sensitivity. Now, so another part will be like what your friend said, you can check. Now, how will be sensitivity of magnitude of Hj omega to particular omega 0 at entire frequency band. You should just get derivative and then plot it with respect to omega. So this actually will show you. You can plot it using MATLAB, you can plot it using a circuit simulator. This will show you how this will be a function of Q. You can plot it for different value of Q. That will show that. Okay, so one thing was remained from last lecture, which was related to transmission zeros for elliptic filter or any sort of filter which has zero transmission in the stop band. In that case, we need to have a circuit to implement it. So, for example, if this is I and this is V, I is equal to SC plus 1 upon SL into V, or V is equal to 1 upon SC plus SL into I. So, for each one of them, then we will have a second order. So, the circuit you need to use to reach from signal flow graph. So, this is related to direct simulation using SFG. Because we had a simple integrator, first order. So, this is second order. For that, just I will give you a sample circuit. Actually, it will be good. Suppose if you can design a filter, just think about it. But I think logically it is impossible. You have a filter with a high Q, but it shows low sensitivity in the transition. Any order, any specification, but high Q. See whether it is possible. Okay, so I just through this circuit. So we need to use two integrators, simple, right? So this was one of the single-ended integrator. Now what we do, we put another integrator, and this is having feedback to the first one. So we have now two. So this output will come to the input of integrator. Suppose this is voltage V3, and then second one, this output, will come here, will be one of the input. Another input will be some input voltage V2. And all of them are R. We called it R star in SFG implementation. So now if you solve V3 upon V2 will be minus R1 C1 upon R3 C2 into V into 1 upon into S 1 upon R1 square. Sorry, this should be R star. This is R star square C1 C2 S2 R1 R2 R3 because I used the general case. So this is one of the modules that we can use for second order equation. For example, if I have in general V sorry, here there was a mistake. This is not. I is equal to SC plus 1 upon SL into V. V is equal to, yeah, this was not correct. Nobody said. Okay, so then from here V will be equal to SL upon S2 LC plus 1 into I. Okay, so this is, so now you compare this relation with this. So V is equal to SL upon S2 LC plus 1 into I. So in the same way, then afterwards, by using a fully differential architecture, like what we did last time, you solve the problem of negative capacitor by just changing the polarity. So this is for a specific case of elliptic filter which has transmission zeros, or any other type of filter which has inverse Chebyshev. Yes, yes. Inverse Chebyshev has. Okay, so if you have any question, if you want to discuss something, we'll do it before going to sample data. Because this was review. If you can have access to Showman, I recommend it very much. That's a very good book. Very good textbook, and it has many problems you can solve. It's a very nice textbook. Okay, so what is your background in sampling and data sampling, Z transform? You know everything? Good. You know Z transform. Which year are you in? Third. Okay, anyway, because I want to talk about how this non-ideal sampling will create distortion. Therefore, automatically a little I will talk about this sampling so that you will know. And then more information you can get. It's not very difficult. So I will talk about basics, and then the more you can get from any signal and system book or any DSP book. This concept of sensitivity in high Q filters is an interesting point. If anybody is interested, we can have more discussion outside the class. Okay. So I have kept anyway every day. So you can come and discuss and give discussing about some examples. Okay, so what will happen is, okay, after all, if you have an active filter, we have the problem of this sensitivity to variations. And therefore, what we can do to avoid it, one way will be to make everything to be as a ratio, like multiple feedback to be a ratio, Q is a ratio function of C1 upon C2. But if we want to make everything to be a function of two, say, capacitance, then practically it is not possible unless we choose another approach. So then we'll see how this is possible. But before that, anyway, we want to talk about discrete time processing, what is essentially a sample data system. What we want to do is, we want, instead of using continuous time processing, do it in discrete time. So when we do it in discrete time, then what benefit do we get? When we do it in discrete time, so we have time to store signal somewhere. For example, on a capacitor. When we store it on a capacitor, then we have actually converted signal to a charge. So now we are dealing with charge. So we process charge instead of processing signal. Now, for example, if I want to amplify the signal, I will transfer my charge in such a way, I will have improvement in the value of charge. If I want to improve, after all, the entire processing I do on the charge, and then at the end I will convert it to the voltage. Therefore, instead of transferring voltage between signal stages, I will transfer it between different stages. Another benefit we get is, we would be able to create a platform at which we don't have any resistor, because then everything is capacitor, because I keep charge and then I do the entire processing just by charge transfer. So when we use capacitor only, then now everything will be only a function of capacitors. So now we will get rid of resistor, we will be having only capacitor, so at least area-wise also I will improve it. And then now, because now everything is capacitor, everything will be a function of only clock frequency I use for transfer of charge and value of capacitors. So it is very easy to make it immune to process variations. Of course, providing sampling frequency is constant. But then we'll see how practically it happens and how we can have this. So essentially what we want to do is, because anyway, any frequency, any arbitrary frequency is RC. So just what we want to do is, we want to convert R to be function of some C into some k, and then this k can be a constant. So what we want to just implement this in the form of a capacitor. Therefore, because in R we deal with voltage and current, in capacitor we deal with voltage and charge. Therefore, whatever we do on the current will be converted into the form of charge. So therefore, I should convert my current to charge, because voltage is voltage. Therefore, I should convert my current to charge. To convert the current to charge, this means that I have to convert my signal to charge. And to convert this current to charge means I have to charge a capacitor by current in some constant time. If delta t is constant, therefore Q will be I delta t will be a linear function of I. Therefore, I would be able to establish this purpose. So what do we mean delta t to be constant? Means we use a clock and then always charge this capacitor at a given clock period. Half of the clock period, 1/4 of a clock period. So the purpose is served. So now I convert my current to a charge. I keep delta t constant. Therefore, this proportionality value will be constant. Therefore, now Q will be a linear function of I. So now the entire processing will be converted into Q domain. But when we do this, what will happen for frequency? So till now, whatever design we do, we design anyway some at j omega with some phi j omega. But now what will happen for this? Because now signal changes, therefore this transfer function also changes. But why we know that we are able to retrieve signal is because of Nyquist theorem. It says that if we are able to have a signal with limited bandwidth, therefore it should have a limited bandwidth. If I have a signal with limited bandwidth, I am able to retrieve it from sampling. What is sampling? Sampling means that same thing we want to do here. That's why these two are related. If I have a signal in time domain, here what we wanted to do, we wanted to convert current to charge. Therefore, we want to charge capacitor in a given time and leave it as it is. What did it mean? Means that I want always to get a sample of my signal in the form of current at some particular time stamp, repeat it after some given delta t and continue. Now Nyquist say that when you want to sample, instead of sampling just simply by multiplying by 1 at a particular time, which is not actually possible in physical system, but suppose if it was. This says that this doesn't help unless you use an impulse function to multiply the signal, not just 1. What impulse function does? Impulse function, according to Fourier transform, it will repeat the signal. If you have a train of impulses and multiply signal by that train of impulses, you will get this. In time domain. And in frequency domain is just repetition of the frequency band. And Fs is actually 1 upon delta t. This is not very difficult to prove it because this is a periodic pulse with this frequency. Of course, magnitude is not constant. It depends on xt. But it's actually xt multiplied by a periodic signal. So therefore, in frequency domain, they will get convolved. You know convolution. Then it will be shifted. Okay, so then everything will start from here. Therefore, I will have a signal. I want to sample it. First, ideally, I can sample it by a train of impulse functions. And t is equal to 1 upon x. So now at the output of multiplier, I will have sample signal. So in frequency domain, oh my god, these two will get convolved. And this conclusion means shift. So therefore, if I can sample my signal by a train of impulse functions, I would be able to generate this repetitive loops of bandwidth. So this bandwidth of signal will repeat itself. So if it is a band limited signal, then these two don't interfere. Or other words, aliasing doesn't happen. Therefore, if I do all processing in discrete time and after all pass it from a low pass, I would be able to get my signal without any distortion. So this is the ideal case. So I sample it in the form of an impulse function. This means that in fact the current which charges this capacitor should be infinite and it should charge this capacitor in 0 time. So that I will get sample of signal and the capacitor in the form of charge. But this is ideal case. So now what will happen in the real case? In real case, what we do is a sample and hold. First, I will draw the block diagram of a system. First, we want to limit the bandwidth. Sample data filter. So whatever filtering we want to do, we will do using this sample data filter. And then effectively, there is inherently a sample and hold here inside this, because this is a discrete time filter. So now when we get it at the output, we have to smooth it, because otherwise it will be like a staircase. I will show you. Therefore, we will need a smoothing filter. And then finally, it may or may not be required. We will see why it is required. Amplitude equalization. And then finally, we'll get the output. So this is essentially a simple discrete time for sample data system. So we can amplify, we can do filtering and whatever functions we want to achieve using this sample data filter or sample data system. Usually it is used for filter application. See, essentially your signal may be a bandpass signal, right? Therefore, suppose if your signal is a bandpass signal, you put a limit here and call this limit omega b. Now look at your signal as a low pass. No, we should use the low pass. What do you mean band pass? Yes. Yeah. So then it will be like this. So let us suppose I have put this omega b. Okay. So then here I will get it like this. Okay. So this was say omega b. Now I will get it here. Now this will be omega b plus fs. This was 0. So now this 0 will come here. This will be minus. This will be 0, sorry. Yeah, this will be fs. And suppose this was omega 1. Then now this will come here. Nothing. Because anyway it is low pass, right? But it doesn't have also components of frequencies close to 0. In fact, it will create better separation, right? Because in this area it is almost 0. Then the question, if this is the case, can we use, so see, because what does it mean? It means that here we cannot go frequencies above 2. Twice of this bandwidth, right? Because these two should not interfere, right? B should be less than minus B plus Fs. Or in other words, Fs should be greater than 2B. But if signal doesn't have components at 0, does it mean that we can reduce Fs? No. Yeah. See, look, what happens is, in fact, you have a component of this is this side. Therefore, you have a mirror of this signal this side. So this was omega 1. Here you have minus omega 1. And this was the boundary we defined, omega b. So you have here minus omega b. Right? So this boundary is defined as per the higher frequency, not lower frequency. It's a bandpass signal, but the separation is defined as per the boundary of higher frequencies, right? Not this frequency. Therefore, what we see in fact here, this was 0, this was Fs, I will draw it here. This is minus omega b. Okay, sorry, this is not Fs. Yeah. This will be minus omega b plus Fs. This is, we call it bandwidth of this signal, though it is band pass. We are looking at signal as a low pass, and then we define this omega p as the bandwidth of the signal. So you have a band pass signal. You call omega p as the low bandwidth of the signal, right? So nothing happens. So you have put a range. This is the signal frequency range, low pass. Yeah. Yes. Oh, no, then it will be 6 kilohertz. Then it won't be 2 kilohertz. No, just you need to increase your sampling frequency. Because now your bandwidth, effective bandwidth is 6 kilohertz, not 4 kilohertz. See? Yeah. No, wait. No, let us first of all look at this question, and then suppose we are talking about the normal sampling, then bandpass sampling or whatever you say. Okay, so first for the normal sampling, if we have a signal, interesting discussions. So you have a bandpass signal, and we define this boundary as B. So you will have negative frequencies. This is minus B. So now I'm looking at this signal as a low pass signal. Now I sample it. So it will remain as it is here. Then it will shift to Fs, this area. Therefore now I will have this. Right? Fs will be here. Yes, I have to. Here, okay, we will do one thing. See, just ignore this figure. I'm drawing it here. Okay, so this will be Fs. This will be Fs plus B. This will be minus Fs plus B. And this is B. And this is minus B. So what is the problem? So I'm looking at it as a low pass filter. Therefore, still I will have my Fs plus B should be greater than B. And this B is defined as my bond. Okay, so Fs minus B. Therefore, Fs is greater than 2B. Though its signal is bandpass, I'm looking at this. Exactly. High positive frequencies is B, total bandwidth is 2B. But usually in positive frequency, usually we define as B. Negative frequency means you come back in time. Go to yesterday. There is a meaning for that. Okay, now what happens if I have this sample and hold? Therefore, practically what happens is I want to charge a capacitor by current. And this current is a function of the voltage. Okay? Or even you can just consider you have a voltage here, V in. You close the switch. You store the voltage here. You open it. As soon as you open, the value you have on the capacitor will be V in T, NT. So therefore you open this switch at time is equal to NT. So this means that if I continue this, I have this signal. This is not any more multiplication in the impulse response, right? Impulse train. It's not multiplication. It actually is how we can explain this. So this is x, this is xt, and these squares are xst. So I can write xst or sample signal is equal to summation of my samples, which will be x, for example, at some from n between n and n plus 1, I will have xnt, and after that I will have the next one. So each one of them, so for t equal to n minus 1 into t less than nt, and t is 1 upon fs. xst will be equal to x n minus 1 t. So if I want to write it here, I should write it like xt this is a step function. Because now signal is getting multiplied by these pulses. And the value amplitude is 1. Again next pulse, again next pulse. Now, if you increase amplitude of this pulse, reduce t, it will approach to impulse, which was the ideal sampling. In fact, beta of the pulse. Okay, so now how it will affect on the. So we know that if it was ideal sampling, there is no change in the frequency. So we define two types of frequency. One is for analog signal, to see how frequency information will change. And one is, therefore, analog signal will give us analog omega, and sample signal will give us some omega, we call it digital omega. What is relation between these two? It's not fully digital, but it is called digital omega because it's not fully digital signal. If I want to multiply signal, so we will start right from the beginning. So for ideal sampling, then we'll see what is relation between these two. In fact, in S domain, for example, I can call it SA, and here I call it some SP, and then we'll see how this S will be. So ideal sampling, I will have I start from Laplace transform, right? So I want to see how this signal will change in the frequency domain. So I will get Laplacian of this sample signal. So Laplacian of this signal will be this. This is not very difficult to prove because Laplacian is for any signal is defined as this. You just replace, because of delta, you will get this component. So, because this is in the form of exponential into S, we define, this is multiplied by S, we define e to the power minus t into S, t multiplied by S is equal to Z. Because to get rid of this exponential, simple. But actually, this is one thing which leads us to digital frequency. Therefore, if I convert S equal to J omega analog, okay? If I want to write it in the form of digital, it will be T multiplied by omega analog. I call T into omega analog is equal to omega digital. This is just a definition. And if S is equal to sigma plus J omega, analog, it will get converted into sigma plus J omega analog into T. So this is now new omega. So omega digital is defined as per this function. And then now how I explain it? So if I want to explain, therefore x e to the power j omega analog t, right? It is now will be x n t samples e to the power minus j omega t. This is just, I have replaced s by j omega. And this is exactly the same thing that we get repetition in the frequency domain. Sorry, here's 2n. Omega s is sampling frequency. Just a minute, I will write here. So this was the definition. We reached to this point, x n t e to the power minus n t s. Yeah. And z is defined by this, therefore x n t z to the power minus n. Now here, okay, so this was general, therefore Laplacian sampled signal is equal to h x sampled as a function of t sampled as a function of s. Here we converted by this definition, z is equal to e to the power minus s t. T is period of the clock. Therefore, we call this in the form of x z as a function of z, which is called z transform. It's actually Laplace transform. It's just matter of convention and changing the notation. Therefore, here, so the xz is equal to this. Now, if I replace, so here is actually, it's based on this. If I replace, this is z is equal to e to the power j omega a into t is equal to x n t z to the power n, which was omega, sorry, analog t into n. And this is omega s, and omega s is equal to 2 pi upon t. So this is ideal case, and this was repetition of signal because of convolution. Now we don't have it, and we have this. Multiplication by these unit pulses. Therefore, here, if you notice, if I have, because Z is equal to minus ST, where are poles in a real filter? Poles will be here. Poles always will be left side of S plane, left side of J omega axis. So either real or imaginary. But zeros can be also on the axis, or even they can be right. Now what happens is, all poles which are at the left, if I use Z is equal to e to the power minus J, let us just consider minus ST. So because the Z is plus. If sigma is negative, then means that magnitude of Z will be less than 1, right? Therefore, by sampling, just what we do is we map this area to a circle. And unit is 1. So this is omega, which is sigma. So Z is equal to e to the power minus plus st. Z is equal to e to the power sigma t plus e to multiply by e to the power j omega t. Since sigma is less than 0, therefore magnitude of Z will be less than 1. And maximum it will be 1. Therefore, all poles which are on the left will be inside unit circle. Don't call it sigma digital, call it sigma star, omega star. And if this was omega analog into T is equal to omega digital for the sake of simplicity. Means that now in frequency domain, if I draw it versus omega digital, if I have a signal which has been sampled and is repeated, if this is 0, this will be 2 pi. And so, this is just for simple. Okay. So this was ideal sampling. And now what happens if I have a transfer function? Suppose you have a transfer function in analog domain. And then we want to see what happens in the digital domain. What happens for this frequency spectrum? In other words, if I have an HS, what will be the equivalent HZ? So, but this might look very complicated now. So right now we keep it as it is. We'll see how this transfer function mapping can be done in discrete domain. So I tried to give a review, but it was very fast, I know. But is there anything that you want me to repeat? to understand better? Because this is a part of signal and systems. See, what you need to do is, see, we sample a signal, that is clear. If it is ideal sampling, it will be a train of impulses. Because of that, there will be multiplication in time domain, convolution in the frequency domain. Therefore, it will repeat itself. And because of this, we will have a new notation of Z, which is in fact same as Laplace transform. Only what happens is this Z is an exponential function of S. S was the frequency in analog domain. Z is the new frequency in the discrete time. But what we should do for filter design, we should design in such a way we are able to map HS, it's some HZ, okay, which is the question, in such a way whatever we do in discrete time can be mapped to analog time, analog domain or continuous time. For that, we need to use this relation between Z and S. See, for example, one simple thing, this simple, very straightforward thing, which is not practically possible. What will be S from this relation? SD will be lnz, right? You just replace S by lnz upon T. You will get Hz. Simple. Now, how to implement this transfer function? That is not possible. Therefore, we need to make an approximation, right? So, if you replace it, what will you get? Implementing a filter with this transfer function. If you want just simply to have a backward in the continuous time domain. So then what we should do? First of all, this was based on ideal sampling, of course, which is not possible. So what we will do? We will use some approximation to be able to get proper transfer functions where we are going from S domain to Z domain. But if it is but possible, then the problem would have been solved, right? Let's see if I don't have that ideal sampling. Now what will happen for the spectrum? Okay, I will write it and then you just tell me, like, can you derive this or not, otherwise I will do it. So, now we have a sample and hold signal, okay? So, it is a real sample and hold. We have some analog signal. And we sample it. So, this will be in general. Thank you. Okay, what you do is get Laplacian from both sides. These are samples. Therefore, after all, this T will be NT, right? Because I want to use this signal. So, this is NT, this is N plus 1 T. So, this T should be replaced by NT. So, then this will be like a constant. And get Laplace transform of this, which will be 1 upon s, u will be 1 upon s. You have a shift of minus t, therefore in frequency will be minus nts. Here you have shift of n minus 1, therefore here this will be minus nt. Oh sorry, this will be plus because this is minus. This is a plus, right? E to the power, so this will be minus n minus t minus n t minus t into s. After all, if you simplify it, you will reach to this. 1 upon s, 1 minus e to the power minus t into s. And that original xnt e to the power minus n t into s. This was that original z transform, right? Now, considering z was e to the power t into s, from here this Laplace transform will be just I want to show you how this will change. S into t into s xz. So we have x s z, right? Ideal sampling. Now this will get multiplied by this term. This means that because of this term we are getting some distortion. So what is this? 1 minus e to the power ts upon s. This is actually transfer function of sample and hold. If you consider you have an ideal sampling system, you will have this. Now you convert it to a sample and hold, you will have this multiply this, right? And it's linear. Therefore, this will be transfer function of sample and hold. So any sample and hold system behaves like a linear system, but it creates nonlinearity because this transfer function is e to the power st upon s, right? So e to the power st. So this is some sort of nonlinearity. Even suppose this was a small, it's like an integrator. It's just like you are giving your signal to sample and hold, but it's integrating it, therefore it is changing the signal. So now we have to do some assumption and then design the filter in such a way this distortion would not be of significant effect. This is one of the reasons sometimes we need equalizers. So then we will, you replace s is equal to j omega and then you see how this will affect on the spectrum of the signal. If you will replace s j omega, then you will have a trend. Yes, this is minus. Okay, there is a little bit maths here, but it is good to understand how this comes. You know, how really do we transform from Z to S? I have not reached to that region, that area still, but at least now you know that, okay, what happens in a real sample and hold system. So this is actually what happens in a real sample and hold. Okay, so then remaining with